Okay, so here's where we were last time. We were talking about linear transformations. Just a quick reminder of the definition. A linear transformation is a function, fundamentally. The domain has to be a vector space. The target has to be a vector space. And then the linearity condition, the thing that allows us to use the term linear, is this thing right here, or, pick your favorite equivalent from below. So anyway, that's arguably the big requirement. Just don't forget to check that the domain and target are vector spaces. Okay, so we talked a little bit about lingo. We talked about usage of the term linearly and how it, very often the term linear is going to be used when it's just a lot easier to say it in a different way, but all they're really saying is linear transformation, right? So heads up, this is going to come up a lot. It's just a lot easier to say things in a way that doesn't involve explicitly saying, here's a function, and by the way, it's a linear transformation. Okay. And then we went through this tedious, it's not that bad, but this brute force, I'll say, calculation confirming that this function right here is in fact a linear transformation, explicitly showing that a linear combination of inputs gives you a linear combination of the corresponding outputs. Okay, so that's where we ended last time. So moving along. We are going to do a lot of stuff with linear transformations, this being as it is a course in linear algebra. And that's nice. You will see lots of linear transformations, but don't just assume that every function that we're going to see in this course is actually a linear transformation, right? Of course, there are plenty of functions that are not linear transformations. Just as a quick for example, here's a function from R2 to R1. Unremarkable function. Wouldn't have batted an eyelash at this function in a multivariable calculus course, right? You see it in this class. Well, okay, yeah, but it's not a linear transformation. And it is easily confirmed that it is not a linear transformation because, after all, if it were, these two things would need to be equal, right? If the function truly did commute with linear combinations, or even simpler, as we're using here, if it were to have the property that it commuted with scalar multiplication, well, this thing here is equal to 4, this thing is equal to 2, not equal, therefore not a linear transformation. So anyway, something to keep in mind. Students, by the way, sometimes ask, well, how come I can sort of just come to my conclusion with an example here, whereas over here I had to use actual algebra. Why don't I have to do algebra here? Or sometimes instead, can I just show an example here, right, in proving something's linear? So the big difference here is that to be a linear transformation, a certain property has to be held always, right? So if you want to show that something is always true, you got to give a general argument. If you want to show that something is not always true, you're not trying to show that it's always false. Right? You're just trying to show that it's not always true. And so because of that asymmetry, a single counterexample in the case of proving something's nonlinear is fine and dandy. Okay. Alrighty. So moving along, I'm just going to show you a bunch of examples of linear transformations. The purpose of this is to kind of reorient your thinking about, what do linear transformations look like? If you are currently thinking, well, there you go, that's pretty much what linear transformations look like. Linear powers of the input variables, something like that, right? They don't always look exactly like that because the domain is not always Euclidean and the target is not always Euclidean. So this is not sort of cosmetically all you need to know. So here's a great first example. That is this function here. I'm going to call it D. Side note, we're going to do a lot with this linear transformation. So this is both an example and an introduction to something we'll do a lot with. D is the act of differentiation. what d does is it takes the derivative. So specifically, this d, if you give me a differentiable function f, the output, what d does to that differentiable function f is it returns this function called f prime. So that's you might think of d as being the act of differentiation. So I claim that this d is linear, even though it doesn't cosmetically look like that example that we did last time, right? This isn't like, constant times x, constant times y, and, stuff like that. So the way we confirm that this is, in fact, a linear transformation, weird though it is, we really should always confirm, well, that's a vector space, that's a vector space. Let's get that out of the way. And now we just have to confirm the linearity property. I need to confirm that if I differentiate a linear combination, that what that gives me is that same linear combination of the individual derivatives. Right? So let me say that a little bit differently. If I put in from the domain, if I put a linear combination of inputs, right? Certain linear combination here of inputs. What comes out in the target is that same linear combination of the otherwise outputs. Okay? So this is all I need to show. We'll walk through the algebra to confirm this in a moment. But linear combination in, linear combination out. Okay, so let's walk through the algebra. This first step is just an observation. This is what D is. D is the act of taking a derivative. So that's just plug it in. Secondly, excuse me, how do I get from here to there? And I'm going to say Calc 1, right? So I hope y'all remember, there was a bunch of boring properties of differentiation that got written down at some point very early on in a Calc 1 class, and the derivative of sum is the sum of the derivatives, and very quickly you just kind of get accustomed to, well, yeah, that's how you do derivatives, and you almost kind of forget that that's a property. You almost take it for granted, right? But if you look back in your single variable calculus notes, you will find that there is somewhere written down is the fact that differentiation of a sum is the sum of the individual derivatives. And a differentiation of a scalar times a function is the scalar times the individual derivative. So, Calc 1. And then I just observe that, well, look at that. That is exactly the definition of D of F1. And look here, that is exactly the definition of D of F2. And so as required, linear combination in, linear combination out, check. That is indeed a linear transformation. Everybody see the process? Any questions? Feel free. I do have there's a question that I regularly get here that if nobody asks, I'll go ahead and ask it rhetorically and answer it. Okay, so here's the question that I get a lot. A lot of people will say at a time like this, okay, wait a second, you're telling me that a derivative is linear. Wait a minute, I know lots of counterexamples to that. We learned way long ago, for example, that, the derivative of sine x is cosine x. This then is the derivative, and that is obviously not linear. So what gives? Right? If you say derivatives are linear, surely not. So there is a subtlety of misinterpretation here, and it's very important to make sure that you're aware of what the problem in the misinterpretation is here. And it comes down to looking at, let me highlight again. So we have this function D, operator, you might say, because the inputs to it are functions, and differentiable function in. The derivative comes out. Very importantly, when we say that differentiation is linear, I'm talking about this. right? That's what I'm claiming is a linear transformation. This purple operator is linear. I am not saying that that function, f prime, is linear. Oh, of course not, right? Again, plenty of counterexamples, very easy. Cosine x is an easy one. So keep. Want to make sure to keep your interpretation on the right thing. The act of differentiation is linear. The resulting derivative that comes out of that act of differentiation, definitely not to be assumed to be linear. Okay, are there any questions about that? Does everybody follow the distinction there? Okay. All right. Okay, there's loads of other examples that I'm going to show you here. This next one, I'm going to leave the actual demonstration as an exercise. It's a lot like this argument that we just made. So here is the result, though. This function here, our old friend from Chapter 1, reinterpreting a matrix as a function. Right? And I really had to fight with myself all the way through Chapter 1 as we were using this to not say interpreting the matrix as a linear transformation or this linear transformation or something like that, because it is. This is a linear transformation. I couldn't say it because, of course, we hadn't defined that term yet. So exercise for y'all to confirm that this is a linear transformation. Like I say, the demonstration is going to look a lot like this argument that we just did here. You're going to look at a linear combination of inputs and confirm that you get the corresponding linear combination of outputs. You're going to use long established facts about algebra that we already know how to do. Up here, it was old established facts about derivatives and stuff. Down here, it's not going to be derivatives, but you're going to be using old established facts about matrix algebra, what we already know about matrix algebra, properties we've already established of matrix algebra. Okay, so that said, strongly analogous, great practice problem. Make sure that you can do that. We're going to go on to the next one here. So this is another weird one. It's important to see a certain number of weird examples because that's really where the power is in the power in an abstract idea is in how broadly it applies, right? So the weirder our examples, the more broad we are able to apply the tools. So here's a linear transformation. This is defined in an odd way. S is the name of this linear transformation. The input to this linear transformation is going to be a function, specifically a function out of this known vector space, C infinity. Hope you all remember C infinity. This is the collection of functions that are infinitely differentiable, defined on this interval from A to B. And the output is that formula, which if you think about it for a moment, we've got this function f defined on this interval from A to B. This is a continuous function, among other things, and it's defined on an interval from A to B, and this is a Riemann sum integral that I can compute out in any of a number of different ways. And what kind of a critter is this? This is a number. Right? It's tempting to think of integrals of functions as other functions. Not really. Those are antiderivatives. This explicit integral from A to B of this given function f is a number. Right? So what we've got here, this S thing that I'm defining is kind of an operator. It goes from this vector space C infinity to this vector space R1. Right? Inputs and outputs. There's the formula for how to do it. I claim that this is a linear transformation. Right, now again, I'm certainly not saying that every antiderivative is a linear function of x. Oh, no, certainly not. Not even close. Obvious counterexample. I'm not saying that antiderivatives are linear. I'm saying that the act of doing this integration is linear. Okay. So, easy, well, it's a good practice problem argument. Now, I'm not going to do this one for you. I am going to do for you, though, one that looks a lot like this. That's what comes next. I'm going to do this one for you. And then I want y'all to do this one on your own. Again, sort of by analogy. Again, great practice. So let's talk about this down here. This function called SG. Notice the G. G is a function that needs to be given, some continuous function. Notice that it's going to play a role in how SG is computed. Right? So what this SG function does is if you give me a C infinity function f, put that right there, and then this is a formula for how to compute this output value in R1. Okay, so again, it's kind of an operator. Right? We've got function in, number out. There's a formula for how to compute it. Now I'm making the assertion that this function, this operator SG, is linear. Okay, let's prove that right now. Okay, let me slide over here where I have a little bit of space to work with. Okay, so what I need to do is I need to compute SG of C1F1 plus C2F2, and I'm going to compute. And when I get done with that, what I'd better get, if I claim that this is linear, I'd better get C1 SG of F1 plus C2 SG of F2. So this is the structure of the argument I'm about to make. Linear combination in, linear combination out. Right? That said, let's do it. The definition of SG. Okay, well, it was the integral from A to B of, well, let's see here. The integral from A to B, I've got the function and then times this fixed G thing, whatever that is, and then take an integral. Okay, so C1F1 plus C2F2 of x times G of x dx. How do I evaluate that function? There's this function called C1F1 plus C2F2. How do I evaluate that? Well, okay, we have rules for that go way back. This is C1F1 of x plus C2F2 of x. Right? What I've done here is just rules of vector spaces. What is the formula for computing that linear combination of functions? Okay. Times G of x, of course, dx. Okay, next step. Let's do a little bit of algebra. Let's multiply all of this out. I get integral from A to B, C1 F1 of x, G of x, plus C2 F2 of x, G of x, dx. That's just algebra. No tricky curves there. Now, flash back to, again, Calc 1 and all the boring properties of integrals that got written down at some point. I can rewrite this as, let me give myself some space. Well, I'm going to break this into two separate integrals, and I'm going to factor out these constants out of each of their respective integrals. And the punchline, I get C1, integral from A to B of F1 of x, G of x dx, plus C2, integral A to B F2 of x, G of x dx. So, like I say, a little bit of Calc 1 there. And lo and behold, check it out. That is exactly SG of F1. And that is exactly SG of F2. And so, as required, we've done the proof. This thing here, whoops, I wanted to go into highlighter mode. This thing here is a linear transformation because linear combination in, linear combination out. There you go. Any questions? Really, the hardest thing about these questions tends to be making sure that you start the argument, that making sure that you ask the right question, making sure that you correctly interpret what it should mean for SG to be linear, namely, put a linear combination of its inputs in. Make sure to interpret correctly what are its inputs. Its inputs are functions, not x's, right? A lot of people make that mistake. And then make sure that you get the appropriate linear combination out. Again, interpreting correctly what that linear combination should be. The actual mechanics of the calculation are usually kind of nothing to it. This is just the definition of SG. That's no big deal. Here we had to remind ourselves how vector spaces work. That was, sort of Math 216 material there, but going way back. This is just algebra. This is just calculus. And then it's just a matter of recognizing that we are in fact done. So the actual mechanics of the doing it is very straightforward. It's the interpretation that you have to be careful about. Pause for questions. Anybody? Okay. All right. So now I'm about to erase all this because it takes up a lot of space, and y'all have had. I hope you've had a chance to copy this down. If you haven't, of course, you can go to the recording that we are currently making and see it at your leisure. Okay. All right. More examples. So this is kind of a weird one, but if you give me a function, C infinity, not that it needs to be, and if you determine an output value by the following odd little formula, just plug in x equals 0. Then what we've got is a sort of an operator, right? This thing, delta naught, takes as its input a function and gives as its output a value. So it seems a little weird, but the act of plugging in x equals 0 is a linear transformation. And so that's a linear transformation. Exercise for y'all to confirm that it is. Same structure of the argument as the several examples that we've already done. And it's just a matter of confirming it. By the way, y'all will see this particular linear transformation in other contexts. It comes up in 353. It comes up a lot in a lot of engineering situations. I certainly saw it a lot as an undergraduate physics major. So this commonly gets referred to as the Dirac delta function. And there are misinterpretations that abound in exactly what this is. And I think the best way to think about it, or certainly a very good way to think about it, is think about it. Don't think about this thing as being a function of x. A lot of people like to think of this as being a function of x. It's really not. It's a linear transformation per this formula. Okay. Related to that, if you take a function and don't just plug in x equals 0. Maybe take some derivatives first and then plug in, maybe x equals a instead of x equals 0. That action, you can think of that as being an operator, and that too is linear. And that too is easily proved. Same structure of argument. Great practice problem. Make sure that you can do that. Now a call back to one that you've already done. We did. It's in the notes, and it was done in the pre-lectures. But way back in Chapter 4, when we were looking at these kinds of differential equations, what we called linear differential equations, note the usage. Here's the word linear. That means that something in play there is a function somewhere in this conversation, identify what is the function being discussed, and then interpret from this usage that this is in fact a linear transformation. That's the function that we're talking about, and my use of the term linear is to suggest that that is a linear transformation. So now again, go back to the lecture notes. I think it's the very first page of lecture notes on chapter 4. I write down a proof, gory, of details that demonstrates that this L is in fact linear. We just didn't say the word linear transformation at that time. But go back and take a look, and sure enough, this is already done. Okay. So there's various little bits of work that have to get done now before we can start doing important things with linear transformations. So I just need to lay some groundwork. So let me apologize in advance. This is going to be kind of hodgepodgey for the rest of today's lecture. But then we will be able to do some pretty neat things after that. Yeah. Anyway, so here's the first little miscellaneous thing that I have to get said. If you have a linear transformation, if you have a basis in the domain, don't forget the domain's a vector space. Don't forget what a basis is, right? Basis is an independent set of vectors that spans the vector space. We've already seen that a basis is a convenient way for describing vectors in the vector space. Interpreted appropriately. So yeah, if you've got a basis for the domain in a linear transformation, linear transformation T, if you tell me all of the outputs, if you tell me the images of those basis vectors, then I claim that in fact completely determines every value of the entire linear transformation. And this is a shocking assertion if you really think about it. Let me try to elaborate on why this is so shocking, right? We've got in this function T, in its domain, there are infinitely many vectors in this domain, of course. It's a vector space, right? It's a whole thing. Right? Infinitely many vectors. I'm going to tell you the value of the function just at a small handful of values. And just from knowing the value of this T at this handful of values, out of the infinitely many values that can go in, I'm going to then tell you all the output values for the whole function. It'd be like a dumb analogy, but let's suppose here's a card trick, and I give you a deck of cards, and I ask you to shuffle it all you want, cut the deck, what have you, right? And then I ask you to tell me the top 3 cards, which you do. And then after that point, I then enumerate all remaining 49 cards. That'd be a good trick, wouldn't it? That'd be a really good trick. That's kind of what this is saying. You give me a very small amount of information about T, I will then give you all of the remaining information about T. Okay. So let me show you how to do this proof. There's really nothing to it. We're going to take advantage of the fact that any vector, here, let me make some different color choices. Every vector in that domain is a linear combination of the basis vectors. This was kind of the whole point of a basis in some sense, right? Give me a vector in a vector space. It, of course, can be written as a linear combination of basis vectors. And with that, let me just write down this little bit of algebra. No big deal here, really, but this vector V, if I were to just plug in that formula for it that I just wrote down, it is a combination of basis vectors. And now let me apply linearity. Linearity says if you've got a linear combination in, you get that same linear combination out. And lo and behold, we're actually kind of done. I now have an explicit formula for this linear transformation T. You give me any input vector V, any input vector, right? Because I've been given the images of the basis vectors from the very start. I was given this handful of values. simply knowing these coefficients gives me everything else that I need to be able to compute t completely. This is kind of shocking. It's as easy as that. Let me show you an example. So suppose we have a linear transformation from R2 to R3. Now there's countless functions from R2 to R3. Countless. Right? About this one, I'm simply going to tell you t of 1, 1, and I'm going to tell you t of 1, 2. That's it. And I'm going to tell you that t is a linear transformation. So with this information alone, can I compute t for other vectors? Well, yeah, sure. For example, just as an example, and following the argument above, 3, 4 is that linear combination of these basis vectors whose images I was given. Well, you got to solve a little system of equations to figure out those coefficients. Those coefficients being this 2 and this 1 here, right? But you can always do this no matter what. Instead of 3, 4, if it had been 7, 8, whatever, there'd be a different set of coefficients. Right? You can always find it. Linearity then allows me to do this, linear combination of inputs, linear combination of outputs, and having been given that these outputs are these, we're done. Right? Knowing those coefficients, I can compute t of 3, 4 like so. Neat fact. Yes? Then you don't have basis. Yeah, no, so this is something that we proved about bases. It was one of the first things that we proved about. Well, no, sorry, this is part of the definition of a basis, right? So a definition of a basis is that it spans the vector space. Another way to say that is that every vector in the vector space has to be a linear combination of those vectors.
So could you include that it's either the vector given a Kernel basis or the vector you're trying to get is not in the vector space? The basis span is the way to distinguish between those space.
I just want to keep my focus on the deal of, so this particular theorem here is saying what if it actually is a basis, and what if all of the images of the basis are actually known. Yeah. So there's various alternate versions of the theorem that what if this, what if that, and that's a thread that you can pull on and you can unravel. It can be a tedious, totally. Okay. Anybody else? Okay. All right. So on to a definition. Define something called the kernel of a linear transformation. Kernel. Here it is. There's the definition. The kernel of a linear transformation is the collection of vectors in the domain for which the image of that vector is 0. Right? So I'm just, notice how very literally and directly I'm interpreting this set builder notation. So the kernel is the set of vectors that hit 0 in the target, you might say, if you want to be sort of succinct about it. Okay, now let me make an observation. For a huge category of linear transformations, namely these, our old friends from Chapter 1, when you say, I'd like to interpret a matrix as a function, we recently realized that these are, in fact, linear transformations. By the way, a little foreshadowing, it turns out in a very broad category of cases, this is what linear transformations look like. Not always, of course. We've seen several counterexamples. All that differentiability business, for example. But for this very broad category of linear transformations, the set of points for which t is 0 Well, that's the set of points that when you multiply by A is 0, namely that's the null space, right? In chapter 2 language, that's all this is the null space. Or in chapter 1 language, the set of matrices, the set of vectors that when you multiply by A you get 0. Well, that's the set of solutions to AX equals 0. That's the set of homogeneous solutions. Okay, so this construction of the kernel is a familiar concept. Which brings up the question of, okay, well then why do we need a new word, right? I mean, if kernel's the same as null space, then why talk about kernels? Why not just say null space? It's just a point of language. The term null space is understood to refer specifically to matrices. By comparison, the word kernel can be used for any linear transformation, and don't forget linear transformations. I mean, there are lots of linear transformations that are not, in fact, actually matrices. Okay. All right. A more explicit example. Let's look at this one. There's an explicit matrix, right, that I'm interpreting as a function. I claim that what this does is this projects vectors in R3 vertically to the xy plane. This is easy to see by just rewriting this formula. Rewrite this as t of x, y, z equals, and then we'll just multiply this out, and what you find you get is x, y, 0. Right? So what this function does is it throws away the z coordinate. Right? So you might say geometrically what this function does is it smushes everything down, projects, smushes, whatever you prefer, smushes everything into the xy plane. All right. So that said, let's talk about the kernel. Well, the kernel is the collection of all points whose image is 0. There's 0. What's the collection of vectors that smush onto the origin? Well, it's the z-axis. So, sort of a geometrically satisfying example of what a kernel looks like. Okay. Here's another context where we've talked about kernels without using the term. We thought about this, all this L business back in chapter 4. We've recently observed that these are linear transformations. So let me point out that if we were to ask for the kernel of one of those L linear transformations, the kernel, well, that means we're looking at the set of functions for which L gives you 0. It's just homogeneous solutions. Yeah. So again, now we've talked, back in section 4.2, we spent a bunch of time talking about homogeneous solutions. Didn't really say it as such at the time, but we were studying a kernel at that time. Okay. All right, another little bit of terminology. We've already defined this, but let me just say it again. The image of a linear transformation. We've already defined the image of a function. The image is the collection of actual outputs. Let me observe that this gets said very bluntly and explicitly with this set builder notation. This says the image of a function is the set of vectors in the target for which that vector actually is the value of the function for some vector which is in the domain. Right? So this bluntly says the image is the set of output vectors that actually come out of the function from an actual input vector. Okay. All right, so old idea. This one also turns out for matrix linear transformations, this is a familiar one. Yeah, it's interesting how this happens to be. But here's how that works. Let's think about the image of one of these kinds of functions. Now, in order to do that, let me remind you that when you have a matrix, you can think of that matrix as being made up of column vectors, right? And don't forget, when you apply this transformation, let me say that differently. When you multiply a matrix times a vector, what you're doing is you're taking a linear combination of those column vectors. All right, so let me leave that like that. The values of this function are always linear combinations of the column vectors. So let's think about the image then. Sorry. I'll leave this highlighted. Let's think about the image. The image is the set of all possible values of the function. Okay, let me say that differently. It's a set of all possible results of what you get when you multiply by the matrix. A little differently still. It's the collection of all possible linear combinations of the column vectors of that matrix. It's the column space, right, that we talked about back in Chapter 2. Now, I think this is an interesting thing to bring up at this point. When we studied the column space, we talked about how to find a basis for it, and we talked about properties that it has, and how it relates to relations, and there was a bunch of stuff to say, but what we never really quite got around to saying was, why do we care about this thing? Who cares about the column space? What is it? Is it natural, or is this just a made-up thing? Well, it's very natural, as it turns out. And here's a way to see it. That column space is the image. If you were to take your matrix and very, very naturally interpret it as a function, which we do a lot, the column space is the image of that function. So, very natural. So I like to close that loop. Okay. Now, let's go back to this previous example that we were looking at, this geometric example here. Remember this function, and it projects everything down sort of vertically, if you will, down into the xy plane. Let's think about image. I can see from the picture here, by the way, the image. I mean, what comes out when you take 3 space and when you smush it down to the xy plane? What is the collection of outputs? Well, it's the xy plane. I just smushed everything onto it. So the image is the xy plane. Notice then, in fact, as predicted, that is the span of the column vectors. You look at those column vectors. Here, let me color code better. That first column vector, 1, 0, 0. This second column vector, 0, 1, 0. This third column vector is pretty boring. Well, it's just the origin. But if you look at the span of those column vectors, you do indeed get the xy plane as you're supposed to. Okay. All righty. Okay, so some exercises for y'all to do. We just defined kernel of a linear transformation. We just defined image of a linear transformation. I want y'all to prove that these are both subspaces. Now, as appropriate, of course, don't forget the kernel lives inside of the domain. Right? So it's a subspace of the domain. The image does not live in the domain. The image lives in the target. Right? So I say they are both subspaces. Well, they're subspaces of their appropriate vector spaces that they live inside of. Okay. All right, so good exercises. Let me remind you of some relevant information. How do you prove something's a subspace? That's an old Chapter 2 problem. You prove that it's closed under addition. You prove that it's closed under scalar multiplication. So that applies to each one of these. Now, let's talk about the kernel, right? That calculation, you're proving that a kernel is closed under addition, closed under scalar multiplication. We've actually already done something very similar to that. Not exactly, but remember, we just drew a connection between the kernel, between the kernel and a null space. In a certain, in the special case that you're looking at this kind of a linear transformation, which of course we aren't always, but we've already showed, well, I think we said homogeneous solutions. We've already showed that the set of homogeneous solutions is a subspace. The proof is in the notes. It's back in section 2.2 somewhere. So take a close look at how that algebra plays out. The argument that you're going to make for a kernel more general sort of thing. But the argument you're going to make for the kernel is going to look an awful lot like that algebra that you've already done or that you've already seen in the lecture notes for showing that a set of homogeneous solutions is a subspace. Okay. All right. Analogously, images. Right? We haven't proved that's a subspace yet, but an image is a column space. Let me say that a little bit differently. An image is a span. And what we have done back in Chapter 2 as well, I think it was a recommended, I don't think I wrote out the actual proof, but I made a recommendation, a good practice problem was to prove that a span is always a subspace. And so the argument that you're going to make to show that an image of a linear transformation is a subspace, it's going to look a lot like that one. So if you're not sure how to get started on this, start with this. Start by proving, again, go back to the lecture notes, there's a practice theorem stated in there, proving that a span is always a subspace. Do that one first. And then structurally, this will look a lot like that. So I think those are really good practice problems, and I think those are really good connections to try to connect. Okay, moving along. Neat fact about linear transformations. If you have a linear transformation, very importantly, little subtlety, if your domain is a finite dimensional vector space, it's got to be finite dimensional. This just doesn't work otherwise. But if you have a linear transformation on a finite dimensional vector space, then the kernel and the image have a relationship with each other. This is very surprising. Don't forget, the kernel lives in the domain. The image lives in the target. These two things live in different worlds. But they still have a strong relationship, in that their dimensions add up to the dimension of V. Dimension of V itself. So this is, like I say, a surprising result. I'm going to prove this for you right here. The dimension of the kernel plus the dimension of the image is equal to the dimension of the domain. I say I'm going to prove it for you. I'm not quite going to prove it, but I'm going to come really close. Really close. And I'm going to finish the proof in a few days. I'm going to make a micro assumption here momentarily, and then I'm going to fill in that micro assumption later on when we have more powerful tools to work with. The micro assumption that I'm going to make is that every linear transformation on a finite dimensional domain can be written as a matrix. Now, not obvious. We've seen plenty of linear transformations that we have not written as matrices. We have also seen plenty of linear transformations that cannot be written as matrices. But it turns out that if you have a finite dimensional domain, that even if you haven't thought of it that way, they can, in fact, all be written as matrices. We'll prove this later on. We're going to prove this in section 5.3. Take us a little while to get there. It'll be next week, if I remember correctly. But so this is my asterisk, right? A little quickie assumption. And then let me point out that, well, for matrices, right? I already know that kernels are null spaces, and images are column spaces. If you've got a matrix, right? I'm assuming, and we'll prove later, that in fact we are dealing with matrices, in effect. And for matrices, we already know that null space and column space are related, that the dimension of the null space and the dimension of the column space adds up to n. So we've already proved this fact for matrices. So all I owe y'all at this point, and like I say, we'll get to this probably next week. I just need to convince you that every linear transformation on a finite dimensional domain can be written as a matrix. And with that one little final bit, we'll be done with this theorem. Okay, see y'all later. Have a good Wednesday.